Hello students, I am SK Dubey from KV1STC again to deliver a lecture on my topic based on current electricity. Today we will discuss application of Kirchhoff's laws. In my last two lectures I explain you Kirchhoff's laws and its application. Some numerical problems is already discussed which are based on Kirchhoff's laws for complex circuits. Today I am here to discuss some other application of Kirchhoff's laws, especially the Wheatstone bridge and Meterbridge. We all know that Wheatstone bridge is a network of resistance and it is developed by Charles Wheatstone to measure the resistance of a wire, unknown resistance you can say. So first of all we discuss about Wheatstone bridge. A Wheatstone bridge consists of four resistors that are connected in shape of a diamond with a supply of source. As you see in this figure, the four resistors P, Q, R and S are arranged along the arms of a quadrilateral, and the fifth one you can say here the resistor G, which is a resistor of a galvanometer along one of its diagonals. The working of this Wheatstone bridge is based on the null deflection. Null deflection, that is the ratio of their resistances are equal and no current flows through the galvanometer. Let's see some more things about the Wheatstone bridge. As it is already told and informed to you, Wheatstone bridge having four resistors. So let's see what is the you can say significance of these four resistors and what the fifth one connected across the diagonal. The working is based on the null deflection, means no deflection in galvanometer. It will take place only when the potential at B and potential at D is the same. In order to get the condition for this thing, when this galvanometer shows null deflection or when the potential difference between B and D is 0, let us consider the network. Across AC we connect source of EMF, that is the cell, along with the battery. Say this cell deliver a current I which flows in this network. But as I informed earlier, when we apply Kirchhoff's rule to any network, the first thing we should keep in our mind about the junctions and where the junction rule can be applicable. When we consider that the current I flowing from the cell reach to A, which is our junction point, So there are two other branches, one is AB and other is AD. So if we consider this out of the current I, if I1 flows through where? Through P, and the remaining I minus I1 flows through R. Again, when this I1 reach to B, B is also a junction point. So for this junction again we distribute the current. Let's see, Ig will flow through the galvanometer, and the remaining I1 minus Ig will go through the resistance Q. If we consider the junction D, these two currents I minus I1 and Ig are coming to the junction D. So naturally the current leaving the junction, that will be I minus I1 plus Ig, the sum of the two. Similarly for the junction C, these two branching current came here, and the total sum I will move out from junction C. So we can say the current through the arms are assumed by applying Kirchhoff's junction rule. According to the Kirchhoff junction rule, we distribute the current first. Then we apply the loop rules one by one. So if we see here, one of the loop ABDA is here. So let's apply the loop rule for this loop, which is named as ABDA. And according to loop rule, as we know that the sum of potential difference across the loop, closed loop, is 0. So the potential difference here, there is no source of EMF here. So the potential difference across the resistors are nothing. It is the product of current and resistors. So I1P plus IgG minus, negative sign is taken because the current direction is opposite to movement direction, and that's why minus I1 into R is equal to 0. Similarly, we consider another loop which is named as BCDV. So for BCDV, according to the loop rule, the equation will be I1 minus Ig into Q, because the direction of current is same, but these two currents direction, one is the current flowing through S and other current flowing through G, are in opposite direction, and that's why negative sign is taken. So now we will have two equations for two closed loop. The condition when Ig is equal to 0. Now we consider the condition for null deflection. When Ig is equal to 0, the bridge is said to be balanced. And when it happens, when we adjust the values of these resistors in such a way that the potential at B and potential at D are equal, then the bridge is said to be balanced. By substituting Ig equal 0 in these two equations, and after manipulating above two equations, we will get what P by Q is equal R by S. So this is the condition for the ratio of the resistances when the Ig is equal to 0, or in vice versa, we can say if the ratio of resistances are equal, then only the Ig is equal to 0, and the bridge is said to be balanced. This is a very important relation which help us to determine the value of unknown resistance. So this is how S is treated as usually, you know, we will see in its application part Meterbridge. S is treated as unknown resistance. So value of unknown resistance can be determined. Now the question is, this is principal part of the Wheatstone bridge. We will see how we realize it, how we construct this meter bridge. The four resistors connecting in arms of a quadrilateral, and then diagonally galvanometer is connected. So the next part of this lecture is toward meter bridge. It's a very simple apparatus, and you can say it is the simplest practical application of Wheatstone bridge that is used to measure the unknown resistance. A meter bridge, as you see here, there are two L-shaped metal strips and one plain metal strips, rectangular metal strips is lying in between. And this AB is a 1 meter long wire. So you can say a meter which consists of a wire of length 1 meter, which is of uniform cross-sectional area, and it is still taut and clamped between two thick metallic strips bent at right angles, as you see in this figure. And there is another metallic strips creating two gaps, and across these gaps resistors can be connected. Left side gap is said to be left gap and right side gap said to be right gaps. So across these two gaps we connect the resistors. One, the known resistance, which can be applied through a resistance box. So resistance RB is the resistance box here. Another gap is connected by means of a wire of unknown resistance. Now the source of current, that is battery, is connected along the ends of the wire, AB wire, which are clamped on the metal strips. So cell and battery is connected across AB. Now we have to connect galvanometer. So one end of galvanometer is connected to the middle lead of the metallic strips, which is placed between the L-shaped strips, and other end of the galvanometer is connected to a jockey, that is what a metallic pencil, and it is used to slide on bridge wire. So this is what about the construction of a meter bridge. Let's see its working now. The working of meter bridge is based on principle of Wheatstone bridge. Principle of Wheatstone bridge means you can say achieving the balanced condition. Achieving the balanced condition means the galvanometer shows null deflection. So what we will do is, first we apply any known resistance from resistance box, and then we slide this jockey over that wire, and we determine the length for which this galvanometer shows null deflection. So for any given resistance applied from resistance box, say R, if R is the value of the known resistance applied from resistance box, and corresponding to this, say L is the length from starting from A, so AJ is the length which is L centimeter, total is 100 centimeter. So for L centimeter we get null deflection or no deflection is sourced by the galvanometer, and the remaining portion JV will be of length 100 minus L centimeter. When galvanometer current is made 0 by adjusting the jockey position on Meterbridge wire for a given value of known and unknown resistances. So getting the null deflection means now this meter bridge, which is realizing actually it is giving our Wheatstone bridge. So Wheatstone bridge realized here is in balanced condition, and if it is in balanced condition, then the ratio of that known to unknown, that is what, R by X is equal to P by Q. P is the resistance of this portion of wire AJ, and resistance of the JB portion of wire is treated as Q of that Wheatstone bridge. So R by X equal RAJ upon RJB. As these AJ and JB are two part of same wire, so the remaining thing is same. So the resistance is directly proportional to the length of the wire. So RAJ may we write as AJ, that is what, L length, and JV is what, 100 minus L. So from this relation we can determine the value of unknown resistance X equal R into 100 minus L upon L. This L is the length corresponding to null deflection which can be determined, and R is said to be known resistance because we insert it from resistance box. So this is how the Meterbridge work, and its working is based on what, Wheatstone bridge. Here I draw a circuit to compare it with Wheatstone bridge. Where is our PQ and where is our R and S? R and S. Here X is written, so it is corresponds to R and S. This is the one end of the galvanometer, and this J corresponds to this point. You just compare it. Your R across AB and R across BC. Clear? So this is what your resistance across L and 100 minus L, and battery is connected. So just keep this thing in mind, okay, where Wheatstone bridge are formed in this Meterbridge diagram, okay, because then only you are able to answer some questions. R upon resistance across AB. See here, R upon resistance across, actually here AB is written, it is what, AJ, and S upon resistance across this JB. So remember that these length, or you can say the portion of wire is directly proportional to resistance R. Means if R is more, this AJ will be more. If X is more, then this JV will be more. Based on these proportional relations, a lot of questions are asked in examination. So we should have clear-cut idea about it. Okay. Let's see some problem related to that concept also. See here, there is a Meterbridge. The null deflection is shown on the galvanometer, which is at a distance of 30 centimeter from one point. When a known resistance of 10 ohm is connected in parallel with another unknown resistance S, the null deflection shows at 50 centimeter from the same point. So it is asked to determine the unknown resistance R and S. Unknown R is also not given. Look at the figure. Your R is not given, S is not given. What information is conveyed is when only R and S are connected, the balance length is 30 centimeter. And when a resistance 10 ohm is connected in parallel to S, the null deflection shows 50 centimeter. What will happen if anybody asks by connecting some parallel to S, where in which side this jockey is shifted, which side, towards A or towards B? So you have to think about this connection. There is a parallel connection between S and 10, and as we know, the parallel combination of the two resistance will give effective resistance less than the least one. So it should be very less resistance. The resistance in parallel connection of S and 10, the resistance get minimized, that get reduced, you can say. Reducing this value of resistance in right gap will reduce the length corresponding to it. So naturally the balance length gets shifted towards V, and that's why instead of 30 centimeter it will come to 50 centimeter. So like that, as I told you earlier, that null point gets shifted. So keep this thing in mind. Later on I will give you some problem based on the series connection also. So first of all, let's discuss the solution of it. In first case, the balance length is 30 centimeter. 30 centimeter, so very simple it is. The ratio R by S is equal L1 upon L2. L1 is 30 and 100 minus L1, L is what? 70. So L2 is 70. So ratio is 3 by 7. Now as given in second case is what? S के साथ 10 ohm parallel में. So when 10 ohm is connected parallel to S, the equivalent resistance in this right gap will be what? As we know, for parallel connection, the equivalent will be R1 R2 upon R1 plus R2. So it will be 10 into S upon 10 plus S, as you see here. So in the second case, according to formula, R by S is what? S means R by S is 1. So R upon S, S means the equivalent resistance, and 10 into S upon 10 plus S here. So it is equal to 1. 1 why? Because L1 is 50, L2 is also 50, so their ratio is 1. Okay. So here we apply the formula. S means the equivalent resistance. So using this relation, what we get, R is equal 10S upon 10 plus S. And if we substitute this value of R in our first relation, means we have to equate it with 3 by 7. The value of S will come to 13.33 ohm. And if this value is substitutes on equation 1, we get R equal 3 by 7 times of S, that is what, 5.71 ohm. So remaining is mathematics. The important concept is when we connect any resistance parallel to the unknown, the length corresponding to that side get reduced. What happens if we connect any resistance in series of unknown? Naturally, the length from that side is increases. Now, let us consider another problem, numerical or conceptual problem, you can say, that will give you another information. A 20 ohm resistor is connected in left gap and an unknown resistance is connected in right gap of meter bridge. Also, the null deflection point is shifted by 40 centimeter when resistors are interchanged. So, deflection point is shifted by 40 when resistors are interchanged. Resistors in right gap is connected to left gap and resistors of left gap connected to right gap. So we have to find the value of unknown resistance. So let's see what happened. In first case the deflection point is say taken as L1 and balance point gets shifted to L2 by 40 centimeter, means the difference of L1 and L2 is 40. Okay, but their sum should be 100. So by interchanging the resistance, difference is 40, that sum should be 100 because these two are the part of 100 centimeter. So solving these two equations, we will get L2 equal 30 centimeter and L1 is equal 70 centimeter. By substituting the values, R by X equal L1 upon L2, that is 70 by 30, we get 7 by 3. So 20 is the resistance given connected in left gap, that is the value of R. So substituting the value of R, we get the value of X here. So rest is mathematics, you can solve it and you may get the value of X is equal 8.57 ohm. Now our third question is conveying another important concept. In Meterbridge experiment, balance point was observed at J with AJ equal L. The values of R and X are doubled and then interchanged. What would be the new position of balance point? So if the galvanometer and battery are interchanged at balanced position, how will the balance point get affected? I am repeating again, there are two things are asked. The values of R and X are doubled and then interchanged. In that situation, what would be the new position of balance point? If the galvanometer and battery are interchanged at the balanced position, how will the balance point get affected? Let's see what will be the answer here. The balancing condition states that what R by X equal L upon 100 minus L. So X by R equal 100 minus L upon L. When X and R both are doubled, 2x upon 2r is also equal to x by r. So 100 minus L upon L means the balancing length would be same at 100 minus L centimeter. On changing the position of galvanometer and battery, there will be no change because the meter will continue to be balanced whether it is connected in the across one diagonal or other diagonal, so no change occurs in balanced point. Okay, I am throwing a question to you which is for homework. I will not solve here because it based on the same concept. In first question, I will talk about the parallel connection. Here, there is a resistance of 5 ohm which is connected parallel here. No, not this one. If this 5 ohm is connected in series, then you have to solve it and find the value of unknown resistance. Okay, so this is all these things. Thank you.